Hello and welcome to our video on interpreting titration curves. So today we'll be going over the basic features of a titration curve and then how this curve changes depending on the type of titration that you're conducting. So before we start analyzing or looking at any curves, I want you to visualize what's actually going on because then it'll make the whole process a lot more simple. So essentially on the left hand side I have a typical titration curve and on the right hand side I have a very simple apparatus that you'd use to actually make this titration curve. So in the burette, I have my titrant. So that is what we are using as a stock solution. And in my flask, I have the analyte. And as you can see, the pH probe is in the actual flask that's in housing the analyte as well. So as you can imagine, if I undo this tap here, and add little bits of sodium hydroxide. So in this case, the titrant is sodium hydroxide. The pH is slowly going to rise because in here, in my analyte in this case is hydrochloric acid. And my titrant is sodium hydroxide. If I slowly add more and more sodium hydroxide, the pH is going to change. And by change, I mean increase, which you can see is happening here. So essentially, it starts at a very, very small pH, which signifies that there's only HCl. And then as I add sodium hydroxide, it progressively, very slowly increases. It then reaches this crazy steep. So that's the point of inflection. So at about 7, at about a pH of 7, that's the equivalence point. And we'll go over what that actually means in the following slides. But I just want you to appreciate it for now. And then if we keep adding more and more sodium hydroxide, the pH continues to increase. So there are a couple of basic features that you need to be able to appreciate on this curve. So we'll start with the X and Y axis. So the X axis, or the horizontal axis, is the volume of the titrant, and that being the solution in the burette that you're progressively adding. The Y-axis, on the other hand, or the vertical axis, signifies the pH. So that's the reading from the pH probe. And recall from the previous slide that the pH probe is in the flask containing the analyte. So essentially, you're measuring the change in the pH of the analyte as you progressively add more titrant, if that makes sense. There are a couple of other things that I'd like you to appreciate. So the easiest way to determine which is the analyte and which is the titrant is by looking at the starting pH. So that is what we start off with. And if you recall from the previous slide, the pH probe is immersed in the analyte. So in this case, the pH starts off very small, indicating that in fact the analyte is a strong acid. As logic follows, the pH is really small. Another thing I'd like you to appreciate is the equivalence point. So the equivalence point, you may recall from a previous video, is the point in which the moles of the titrant and the moles of the analyte are perfectly balanced. You can appreciate this as about the midpoint in the point of inflection, the point of inflection being where the curve changes in concavity. For your exams, it's high yield for you to understand the changes in the curve depending on the titration that you're conducting, and now we'll go over some examples. So the first one we have is a strong base and a strong acid. So I've written an equation for you to help you visualize this. So in this case, sodium hydroxide is my analyte, and I'll label that as my analyte. And HCl is my titrant. And that kind of makes sense because if you look at the initial pH, it's incredibly high, which means I must be starting off with a strong base, which in this case is sodium hydroxide. Hydrochloric acid is my titrant, so that's what's in my burette, and that is what I'm progressively adding. So with a strong base and strong acid titration, or vice versa, a strong acid and strong base titration, the highest yield point for you to understand is that the equivalence point will always be at pH 7. And that makes sense. You may recall from a video on volumetric analysis that the end product, so sodium chloride, is a neutral salt. And thus, at a pH of 7, the moles of sodium hydroxide and hydrochloric acid will be perfectly equal. And another way of phrasing this is this sentence here. So each mole of strong acid is neutralizing each mole of strong base. So at the equivalence point, if they are perfectly aligned and each mole of strong acid has neutralized each mole of strong base, that means the pH must be neutral. And that is about here on this curve. For your exams, you'll either be asked to find the equivalence point, asked to either appreciate the type of titration that's going on, or asked to find the volume of the titrant that you must add to get to the equivalence point. This is quite similar to the previous curve, but in this case, it's a strong acid and a strong base. So in this case, the acid, HCl, is the analyte, and the base is the titrant. And this also makes sense because you're starting at a very small pH. You're progressively adding more sodium hydroxide. You reach your equivalence point at about a pH of 7 because it's a titration between a strong acid and a strong base, giving you a neutral salt. Thus the pH will be around 7. And then you pass this equivalence point when you add more sodium hydroxide. Ideally, especially for your schools, if you do any titration competitions, you want to be finishing the titration at around between these points. You get a pretty good result. Obviously, the closer to the equivalence point you get, the better. So these pH curves do get a little interesting when we bring weak acids and weak bases respectively into the equation. So there are a couple of things I'd like you to appreciate with this. So initially, we'll start our conversation with the buffer zone. If you haven't already, please watch our video on buffering solutions. You'll get a better appreciation of what's going on. So essentially, with the strong acid and strong base titrations, there was just a smooth, steady increase in the pH, followed by a sharp equivalence point, and then a smooth increase again. With the weak acid and strong base, initially, you can see a really sharp increase, and then it starts to plateau. So from approximately here to there, as we add more strong base, the pH of the weak acid doesn't really change, especially compared to here. So if you look at these 2 points, so from here to here, there's a really sharp increase, but from here to here, not so much. There's a really steady, gradual increase, almost like the weak acid is resisting an increase to the pH. And that is exactly what's going on. So in the first equation, I've written the overall equation for the titration that's going on. So this is a titration between acetic acid and sodium hydroxide, giving you sodium acetate and water. However, I've also written a half equation with acetic acid and what's going on. So acetic acid plus H2O gives you the acetate anion and the hydronium ion. So essentially, if I'm adding a ton of hydroxides in solution, so I'm increasing the basic nature of the solution, the system will, or acetic acid rather, will try and resist this change by forming more hydronium or H+, and thus neutralizing the extra sodium hydroxide that I add. This is only a momentary effect, and this is what we call the buffer zone. The highest yield for you to understand is that the buffer zone is about 1 pH unit on either side of the pKa. Now you might be asking, what on earth is the pKa? The pKa, you may recall from a previous video, is a dissociation constant. The highest yield thing for you to know is that for a weak acid or a weak base occurs at half the volume of the equivalence point. So the equivalence point is about 10 milliliters. The pKa will occur at half the volume. So in this case, 5 milliliters. And then we can track it and find the pH. And whatever value we get for the pH, that will be the value for the pKa. I'll give you a proof for why that is in a following slide, but I just want you to appreciate these features now. Okay, so here's the proof of why for a acid-base titration between a weak acid or base and a corresponding strong base or acid, why the pH is equal to the pKa at half of the volume of the equivalence point. So you may recall from a previous video that there is a relationship that we can draw between pH and pKa, and that's this equation here. So the pH is equal to the pKa plus a log of the concentration of just the ionic form of the acid after it's dissociated over the concentration of the original acid. Now I've constructed a rice table here, and it kind of uses the concepts of the previous graph, so feel free to flick back to that. So essentially we're looking at a system with a weak acid as the analyte and a strong base as the titrant, as in the previous graph. So the definition of the equivalence point is that the moles of the weak acid and the strong base will be equal. So they'll be 1 to 1. However, at half of the equivalence point, for every 1 mole of analyte, I'll have 0.5 moles of titrant. And that makes sense because I have to add another half of the moles to get to this, which is the equivalence point. And that's exactly what I've shown here. So initially, I have my acetic acid, and that's at 1 moles. I have sodium hydroxide, which is at 0.5. And with respect to both of those, I've just put sodium acetate, or of interest, the acetate anion, which corresponds to the A minus. So obviously these two are going to react together, signified by the minus 0.5, and they're going to form this here, signified by the plus 0.5. So at half of the equivalence point, you'll have 0.5 moles of the acetic acid left. You have 0 moles of the sodium hydroxide because it's already reacted, and you have 0.5 moles of this newly formed sodium acetate that you've created. You can then add more sodium hydroxide to get it to the equivalence point, but we're interested about the pH and pKa, so we won't discuss that. So if we plug these values in, so this is my A minus, and this is my concentration of the original acid. If we plug these values into the original equation, we'll get something that looks like that. So pH equals pKa plus log of 0.5 over 0.5, which gives us log 1, which we know equals 0. So thus, the pH equals to the pKa at half the volume of the equivalence point. That's a very high yield association for you to remember. Before moving on to the next example, I'd also like to discuss the equivalence point. So you may recall, an acid-base titration between a strong acid and a strong base will give you an equivalence point that corresponds to a pH of 7. However, in this case, you can see that the equivalence point corresponds to a pH that is arguably greater than 7. And why is that? You may recall from our video on an introduction to volumetric analysis that the titration between a weak acid and a strong base will give us a slightly basic end product. And this makes sense because acetic acid is our weak acid. So its conjugate base, the acetate anion, is weakly basic. So thus, sodium acetate is a weakly basic salt. And at the equivalence point, we won't have any acetic acid left, and we won't have any sodium hydroxide. We'll only have this and water. And since water is neutral and sodium acetate has a pH of above 7, the equivalence point will be above 7. That's a really high yield association for you to remember. So the weak acid and a strong base titrations will always have an equivalence point that will be above a pH of 7. I have another example, but in this case it's a weak base and a strong acid, so we'll appreciate this overall equation here. So I have ammonia as my weak acid and the analyte, and I have hydrochloric acid as the titrant, forming ammonium chloride and water. So again, I want you to appreciate a couple of things. So first, there's a big drop in pH, and between about here and here, it looks like the system is resisting that change. That is what we call the buffer zone. So any titration between a weak base or a weak acid, so if it has any of those two, it'll have a buffer zone. So that's a really high yield point for you to remember. Another thing I want you to remember is where the equivalence point lies. So we've gone through two different examples now. So strong acid, strong base titrations will always have an equivalence point of pH 7. Weak acid, strong base titrations will have a equivalence point above a pH of 7. This is a new example. A weak base and strong acid titration will have an equivalence point that is less than pH 7. And that's kind of contrary to what we explored before. So ammonia is a weak base. Thus, its conjugate acid, the NH4 plus ion, will be slightly acidic. Thus, the product of the titration, ammonium chloride, will be a slightly acidic salt. At the equivalence point, we don't have any ammonia left, we don't have any hydrochloric acid left, we only have ammonium chloride and water. As water is neutral, if we have only ammonium chloride and ammonium chloride is slightly acidic, at the equivalence point, the pH will be slightly less than 7, which is what we can appreciate here. So that's the equivalence point about there. And that is very clearly slightly less than 7. So just remember those high yield points. Now I have a titration between a weak acid and a weak base. So I have ammonia as the weak base, and I have acetic acid as the weak acid. So the highest yield association that you need to make is that there's no discernible equivalence points or endpoints. And just looking at where the pH starts, so in this case it starts at a low pH, but with respect to a strong acid, not that low, so that's a weak acid. That's what I need you to appreciate, just where it starts and that there's no definitive endpoint or equivalence point. So here is a nice table summarizing all the findings from this video. So the type of titration, the pH of the equivalence point of that titration, and if there is a buffer zone present or not.